Hi, I am Satyajit, and I am here to talk about automatic migration from synchronous to asynchronous JavaScript APIs. This is joint research with Alexei Turcott and Frank Tipp at Northeastern University. Let us get started with a bit of background. I/O operations are quite common in JavaScript applications. These can be in the form of file system interactions, database queries, or network requests. And these operations can either be synchronous in nature or asynchronous. The main difference between the two is that synchronous calls block the program execution completely until the result is ready, whereas asynchronous calls return immediately and notify once the result is ready. So why do developers prefer synchronous APIs? So synchronous APIs tend to be quite fast, they're very easy to implement, and they have a straightforward control flow. Refer to this function compress. So in this function, we have a call to zlib.gzip_sync, which takes in an input, compresses it, and assigns the result to the variable output. So this is a synchronous version of the gzip function. And as we can see, it is quite straightforward and easy, and the control flow is straightforward as well. However, this function is blocking in nature, and as a result, while this function executes, no other function in the program can execute, and this makes it non-scalable. So asynchronous APIs, on the other hand, tend to be slightly slower for a single call compared to synchronous APIs. They are much more complex to implement, requiring callbacks or promises to handle the asynchronous behavior. And this also complicates the control flow. So this is an example of the same gzip API, but using its asynchronous version, which takes in a callback. So as we can see, the gzip call takes in the argument, which is the input, and it takes in a second argument, which is a callback function. And once gzip completes its operation, it will call this callback function with the result, which is the output, and we can process it further. So this is an asynchronous call, which makes it non-blocking in nature, and that makes it very scalable. If we compare the performance of a synchronous and asynchronous API, we can see that as the application scales up, asynchronous APIs perform much better. So this is a plot of the number of API calls on the x-axis versus the time it takes to get back the response on the y-axis. And as we can see for a synchronous call, it is slightly faster for a single call, but as the number of calls goes up, the asynchronous API is much faster. It completes 10 calls in about 10 milliseconds compared to about 40 milliseconds for the synchronous version. Now we have handled the problem of scalability, but how can we deal with the complexity of implementation? And async await comes to our rescue for that particular problem. So here is an example of the same compress function using the async await syntax. As we can see, this is very similar to the synchronous version, wherein we had a call to gzip with an input, and the output, the return result was assigned to the variable output. However, this gzip is an asynchronous version, in fact, and it is almost same as the synchronous version, except the addition of the async and await keywords. So async await was introduced to JavaScript in 2017, and this reduces the complexity of implementing asynchronous APIs. So we no longer require a callback function for it. And as a result, we have a much more straightforward control flow for this. And this makes the function non-blocking as well. So in a sense, async await gives us the best of both worlds with the simplicity of the synchronous APIs along with the performance benefits of an asynchronous API. And this brings us to the goal of our project, which is exactly what we've seen with async await example, is that we want to preserve the simplicity of synchronous implementations while getting the benefits of asynchronous versions. And how do we plan to achieve this? So we have gone about this with a three-step approach. The first step in the approach is to identify candidates for transformations. So in our example, we have gzip sync as a likely candidate for transformation. So the first step is to identify these. The second step is to discard transformations that we do not support. There may be some cases in which we cannot transform the code, and we will discuss this in detail in the further slides. And the last step is to actually apply the transformations to those candidates which we've identified. And in this case, it is converting the synchronous gzip call into an async gzip call with an await and making the compress function async. So let us look at the 3 steps in a bit more detail. So the first step is identify transformation candidates. So if we have a look at this program, we have on line 130 at the bottom a call to the outer function with one argument. And this outer function calls the inner function with the list of files. And the inner function calls a map on these files with the read file sync function. Now we start off with a call graph of this program. And from the call graph, first we identify the synchronous APIs. So in this example, that would be the read file sync. And then we try to identify who is calling read file sync. So that brings us to the call to map. And map is called by the inner function. And inner function is called by the outer function. And finally, the outer function is called by the root of the program. And from this information, we create what we call as transformation sets. And this is a sample transformation set for the above program, which gives us a mapping of read file sync to array.map to inner to outer to program root. And we try to create such transformation sets for all the synchronous APIs that are present in our program. The next step is to discard the transformations that we do not support. So in some cases, it may be impossible to transform some code, or we maybe do not support that particular transformation at this time. So an example of this would be, say, a function being called within the constructor of a class. So in this example, we have a call to a synchronous function, and that is assigning some value to this .data. And if we were to make this function asynchronous, so typically what we would do is we would await the call to synchronous call, and we would make the constructor async. But if we try to do that in practice, we would run into an error where a class constructor cannot be made async. So we cannot support this transformation since it's invalid syntax. So there are a few other cases where we do not support the transformation. So one of them would be if a function already returns a promise, or sometimes there are functions which we simply do not support at this point of time. So we would identify such functions from the transformation set and remove that particular sync call completely from our transformation list of transformations. And the last step is to actually transform the code. So we have a set of rewrite rules that we apply to each node within our transformation set. And to get a more formal definition of the rewrite rules, you can have a look at the paper. But in essence, what it does is that if we had a function, say, for example, with compress calling gzip sync and compress being called within an outer function, what we would do is we have already identified the gzip sync function and the transformation set for it. We would apply some transformations based on what the particular node is. So in this example, gzip sync would get transformed to an awaited call to a promise-based gzip function. And since we have now awaited a promise call, we need to make the compress function async. And now since async has become a compress function, it returns a promise instead of data. And so we need to propagate this async await throughout all our call stack. So as we know, the compress is being called within the outer function. Now we need to go ahead and await that compress function call. And lastly, since we're using await within outer, we need to make the function async. And this would complete our transformation for this particular example. Now, in order to do this or suggest transformations for this, we developed a tool called Desynchronizer. So here is a sample output from Desynchronizer. So what we see here is some suggested transformations. And it says that we have changes in 5 files. It identified 11 synchronous functions. And in order to transform these functions, it would have to modify 17 other functions as well. And below, we can see a detailed listing of all the transformations that Desynchronizer has suggested. So let us just have a quick look at this example. So it says that within file eprom.js on line 62, we have a function called to fs.readFileSync at present. And after transformation, we would convert this function call into await fs.readFilePromise. And the entire file would be wrapped into an IFE. So this is the way that Desynchronizer suggests transformations to the developers that they can go ahead and apply. Now, just a word of caution on using Desynchronizer. So as we know, JavaScript is a dynamic language, and this makes static analysis very difficult in it. And due to this difficulty, we get unsoundness in the analysis. And naturally, this unsoundness is likely to trickle into the transformations that we suggest or apply. And as a result, we say that Desynchronizer only provides suggestions, and these should not be applied directly without verification to the actual program. Now, how did we evaluate Desynchronizer? So in order to evaluate Desynchronizer, we ran the tool on 12 randomly selected projects. So this was selected from a large set of programs which had to contain synchronous API calls. We should be able to build them locally, and all of them had to have a test suite which passed. Now, after running Desynchronizer, we automatically applied all of the suggested transformations in the program. And based on these transformations, we tried to answer 4 key questions. So the first question is, how many transformations are proposed by Desynchronizer? And we found that there were 316 synchronous API calls present in those 12 projects. And out of 316, Desynchronizer transformed 256 of the synchronous API calls. And 60 transformations were abandoned. 4 of these were due to constructor definitions, like the example that we saw earlier. 5 of them already returned a promise, and that is something we do not support. And lastly, 51 of the transformations were due to function calls, which we do not support. So programs may use external functions from different libraries, and we simply do not have support for all of them. And we sometimes avoid transforming certain cases like array.reduce, where it would add too much complexity to the code, making it potentially unreadable. The second question that we try to answer is that we know this technique is potentially unsound, but how often does this manifest itself in practice? And we did this evaluation by running the application's test suite. And we identified that only 12 of the 256 transformation resulted in behavioral changes that were detectable by running the application's test. So 9 of these 12 behavioral changes were due to unsoundness in the call graph, and 3 of them were due to some incompatibilities with the test infrastructure. So one thing to note here is that 209 of the 256 synchronous API calls were actually covered by the tests. So that is about 81% coverage for the synchronous APIs that we transformed. The third question that we try to answer is what is the impact of refactoring on the performance of applications? And we have evaluated this by running the application's test suites. And as we can see, the test runs before and after are pretty much constant. So as we can see that this does not negatively impact the application's runtime for applications tests suites. And we consider this a positive result because as we saw earlier that asynchronous APIs tend to be slightly slower for a single call compared to their synchronous counterparts. And these values were averaged over 20 runs of the test cases. And as we know that this does not exercise the application at scale, we do not see a significant improvement in the runtimes for the tests. And the last question we try to answer is that how long does it take to apply Desynchronizer to an application? So this table shows the build time for the call graph and the transformation time it takes to actually transform each application. So what we found is that the time for running Desynchronizer mostly depends on the time it takes to construct the call graph for it. And on average, we found that it takes a few minutes to run this for most of the projects. So switchboard and adapt authoring are outliers in this case and take much longer. And when it comes to applying the refactorings to projects, so this mainly depends on how many related functions we need to transform for each sync API call. And on average, this is quite low and completes in a few minutes. So what are the key takeaways from this talk? So we developed a tool called Desynchronizer, which transforms synchronous API calls into their asynchronous equivalents. We have made the code and artifacts for this project available open source, and there's a link to the DOI in the presentation. And if you would like to get more details on, say, the formal specification of the call graph algorithm or the formal rewrite rules that we use, you can refer to the paper for that. Thank you.